Up next, we have Thomas Nylen from UNAVCO, who will be talking about UNAVCO continuous GNSS station updates.
And thank you for allowing me to speak here today. I will hopefully impart some of our experiences with power systems the last over 13 years. And this is a picture of a site in Antarctica. This is Martin Peninsula in West Antarctic. This is our latest iteration on our power system. Get a pointer here. So we got two panels, a small frame. We have a one box now with vacuum insulated panels with 10 100 amp hour batteries in here, and this weighs about 1,000 pounds to run a GPS system through the year. And in this system now we're using, how do I change the, yep, there we go. We're using a new GNSS receiver, the Resolute Polar receiver produced by Alert Geo. It's been on the market for a couple years now, and we're very excited about this new receiver, mainly because it's low power. If you connect it to a GPS antenna, the power consumption is about 1.4 watts. So in comparison to our older receivers, which are around 3.2 watts, so a big savings in power. And on the right here is just a picture of one of our system boards in Greenland, where we've now replaced the NetRS receiver with the Resolute. And the Resolute has on board a Iridium OEM board, which is packaged together with the GNSS board. And we can transmit data through Rudix, which is downloaded through the Zeos tunnel in Nova Scotia. And we can also push firmware over this Iridium, so we can upload new firmware to the Resolute. And the operation of this is very simple. We can send commands over SBD to make configuration changes to the receiver. So a big change for us, a very new powerful instrument that I will show some examples later on what it means in terms of our power systems and how much we can save in terms of weight and batteries. And I just want to also mention, as Mike said, we have acquired a couple more UAVs, and we're hoping to add some more platforms, including multispectral LiDAR and other type platforms we can carry on these larger UAVs. And one of the nice things about this 210 RTK is it's got an ADS on board that it announces to the user of the UAV and also helicopters or fixed wing that there's a UAV in operation in the area, which was well received in McMurdo this past season. Just to talk about quickly our network, we support about 140 sites in Greenland, Antarctica, Alaska, a few on South Georgia. Half the Iridium network now is the Resolute Polar, as I mentioned earlier. And we still have just a few dial-up sites left, and the rest are Rudix for Iridium communications. And we also have a network around McMurdo of 16 receivers with Tuacom EB1 radios. And this is just a picture of Greenland and the 40 Resolutes, which is part of GNet, and we also support GLSEN, and we got a couple of receivers at Summit Station. In Antarctica, kind of a plethora of sites, but a pretty dense network now in West Antarctic and the peninsula. We're supporting ANET, a UK ANET, which is Pippa Whitehouse and Peter Clark out of Durham and Newcastle universities, and also we have some of our receivers we use for science support. This is just a picture of our radio network in McMurdo. We also support the Kiwis tidal gauge data logger. We download data for them. We also support the McMurdo LTR, a couple cameras in Taylor Valley. Some of our shots here are pretty long. A couple years ago, we helped out Mark Seefeld and his project, connected 230 kilometers through Erebus Deck to McMurdo, and we were hoping to get Fishtail Point on the network, but that was 260 kilometers and 2 repeaters and just a little too far to make that connection. But but a very robust radio network in McMurdo. Now, switching gears to the power systems, this is a picture of Mount Fleming, which is in the dry valleys. It's on the edge of towards the East Antarctic Plateau. This is the predecessor to PoleNet, which includes GNet and ANet. This is a picture about circa 2006, and this is kind of what we built this is the predecessor to it's called TAMDIF, the predecessor to PoleNet, and this is what we kind of started with, and we had to, in 2007, because PoleNet was funded, and we were funded to help them out and produce 40 systems, we had to ramp up quickly to be able to make systems that could be deployed from helicopter or Twin Otter in 4 hours or less. So we had to kind of improve upon this design and make it easier to deploy and quicker. And this is what we came up. This is Ian Dazelle next to our Deverall station, which we installed in 2007. This is a 4-panel system, a larger frame, 22 batteries, 2 Forgin 500 wind turbines, a little met pack, and the iridium antenna. So we were successful the first year in building 40 systems, deploying them rapidly, quickly, and then the next couple of years we learned some hard lessons along the way. We had some failures in the frame, mostly due to the failure in the couplings here on the diagonal supports. So in most cases we replaced the couplings, and we also redesigned our frame to be smaller, which is the same frame you saw in the first picture, which much more durable for the harsh conditions, and we've not had any fail. We've also gone to these marine antennas for the iridium, hardened some of the solar panels. And then some other lessons we learned. This is an example where you don't put the wind power directly to the batteries. This was actually probably degassing the batteries, which then this system board created a spark and blew up the box. Fortunately, nobody was there. Where is that, Tim? This is Iggy Ridge in Antarctica. Another kind of dramatic wind turbine disaster. This is from Tony Mountains, where the wind turbines probably produce voltages over 140 volts. And probably toasted the charge controller here and started a little fire. So we've had mixed results with wind. I won't talk about it anymore, but we've been using the Fortune 500s a lot, and they're about $1,000, and they don't typically last that long. So it's not something you can really rely on when you build your power system. A couple other things we learned along the way. Static is a big problem in these systems. And to try to eliminate static, you can't really get an earth ground in these systems. So to eliminate the static, we put in this little plate here along the bulkhead of the case, and tied in our GPS and iridium bulkheads, put some wires directly to the battery, but also put some wires to our anti-static bag on the system board here, and this has eliminated the problem of static that we know of. Another thing we did that I think was very important is we changed the charge algorithm of the charge controller to match the recommendations from the battery manufacturer, which we used DECA gel cell batteries. So they in red here is their recommended charge curve. Our original UNAVCO charge curve was this green line, which was at warmer temperatures too high of a voltage. So we adjusted the charge curve to match the battery manufacturer recommendation. And we've deployed probably around 2,000 of these batteries over 13 years now. And we've had very few failures of these batteries, so they've been very successful. And I think this has a lot to do with it in terms of meeting and charging them properly over time. We've had these batteries work at extreme cold temperatures. This is in temperature in Celsius. This is a project we supported at South Pole for Michelle Kutnick. The temperature inside the case is down to -60, and this ran for 2 years continuously without losing any data. So these batteries have been successful. They work well. They work at cold temperatures. We've deployed lots of them. We have had some batteries fail, and very few on their own. This is a site in Greenland on the East Coast called Weimer. In early March, when the system started recharging here, the voltages have started going down. Fortunately, myself and Bo Madsen from DTU went in August. We tested every battery using the Medtronic's SCP-100, and we were able to identify 6 of the 24 batteries that were bad, and we removed them from the battery bank. And just after we did that, the voltages started going back up, and the system survived through the winter until we got back next year and replaced those 6 with new batteries. And if we just used a voltmeter, would not have been able to determine these 6 batteries were bad because the voltages were the same for all the batteries. So just to show you a picture, this is the device we use to test the batteries. And now every time we go to these sites, we test all the batteries that we can, and we will eliminate any batteries that deviate from the battery bank. And we've, over the years, pulled maybe another 10 or 12 batteries out from these battery banks by using this tester. So it's a good way to identify bad batteries in a battery bank. One thing to note is this is temperature dependent, so it's hard to compare one year to the next in terms of measurements. So if you were trying to estimate if the batteries are going bad over time or not, it's kind of hard because it varies on temperature. Also, this thing only works when the voltage is 13.8 or lower. So in Antarctica, because of the temperature compensation of the charge controllers, typically the voltages are 14.5, and you got to wait a while for that voltage to go down before you can start using this device to measure the batteries. But it's been a very effective tool for looking at the health of the battery bank when we visit the site. So now I'm going to show a little bit of data from our systems. And this is a worksheet we've developed in just Excel, where we can enter the latitude, the number of batteries. We can put our load in for the system. We can put in the average winter temperature. And the blue line is this is the max voltage, and this is the min voltage over time. So we can use this as a predictive tool. How many batteries do we need at a site? We can also compare it to a site that's been running and see how well it's performing. It's a very useful tool. And this red line is our low voltage disconnect, where the charge controller will turn off the power to either the Rudix modem, or in this now we put the Resolute to the LVD. So this is kind of our threshold we don't want to go below. And this is data from Cap Morris Jessup, which is at the northernmost point of Greenland. And the green is the average voltage over the course of the year. And this is over 10 years of averages. And this is the min and max values. And should mention the site has a wind turbine, or 2 turbines, which are not working that well now. So up to 2018, this is probably more reflective of the voltages through the winter. And as you can see, the system is performing as we expect. It also validates the worksheet that we put together that this in fact matches what we see in the field. And then you can see late about now, the systems are starting to wake up, but there's a little bit of delay. And this is the solar plot of the kind of the solar through the summer. The system's a little bit delayed to wake up early in the spring as the batteries start to charge up and warm up. So this is with our NetRS system. This is a 5-watt system. And then in 2018, we installed the Resolute. We had to put a bias T in to power the GPS antenna. Most modern receivers now require only output 5 volts. And this antenna requires 7 volts, so we had to put a bias T in to produce a little bit more power. So looking at the Resolute now, the bottom of the voltage through the end of the winter is around 12.2, so we've definitely, because of the lower power, have gained a little bit of cushion in this system. Down at the South Pole, Mount Howell, this is very similar system, Cap Morris Jessup, 2 less batteries, but a similar power load, but the temperature is 15 degrees colder. And you can see the effect of temperature has on on the voltage. This system almost ran out of power. This is data from 2018, and probably also delayed the recharge of the batteries because it got so cold and the chemistry might have started to freeze a little bit. So temperature is a big important factor in the voltage. This is a comparison of a site near Thule. This is temperature versus voltage, and you can see there's a pretty good correlation. And just to move on quickly, if you do a multiple regression between the capacity change and temperature, it explains 96% of the variability in voltage. And if you plot the predicted in red versus the actual temperature, you can see there's a very good correlation between the two. Now, if you go back to Mount Howe, and we wanted to install a Resolute this year, but because of logistics, we couldn't. But if we did, we would have lowered the system from 5 to 2.3 watts. And you can see that this now would have been, again, more like Catmorris Jessup. We would have a lot more cushion in the system and above 12 volts. If we're going to install the site as new, if we're going to go today and install it, how many batteries would we need? We originally have 22 batteries. If we had a Resolute, we could probably drop that down to 16 batteries and still have it reach about 12 volts at the end of the winter. If we put in an insulated box, like I showed in the first picture at Martin Peninsula, we could lose another 2 batteries. If we turned off Rudix and only downloaded data during the summer, we could drop that down to 9 batteries. So a big change from 22 to 9 batteries. So this is what the Resolute really provides us, is a chance to reduce the weight, put everything in one box, insulate the box well, and we can start to, logistically make it more practical to get some of these sites installed. For Mark Seefeld's project, install a site at Willie Field. Used this worksheet to estimate how many batteries I needed, came up with 6. And you can see the theoretical versus the actual, and pretty much nailed it in terms of the system through the winter. And this is only 6 batteries and a load of 1.9 watts. And as somebody asked, how can you use GPS to measure snow? Well, this is one way, using the reflection off the surface, which, again, a good use of technology. We always ignored this data. Now people can use this to determine this change in the height near the GPS antenna. Just to note, the footprint here is not very, it's only a couple meters, so you can only measure in a very small area, the snow accumulation. Lastly, this one site for UK ANET, I talked them into buying a Resolute for this site. They could only get 4 batteries there because of logistics. So I'm going to probably turn off Rudix here shortly. Unfortunately, the British Antarctic Survey has their own custom charge controller, and it's been doing some really weird things, which is not too hopeful for the system to survive the whole year. But if it was one of our systems, power systems, we could probably get through on 4 batteries, which is starting to get pretty low in terms of weight. They're 70-pound batteries, so we're talking maybe a 400-pound system. So starting to get really light. So in conclusion, a couple takeaway messages: know your environment, temperatures, obstructions that block your solar recharge. Know your power requirements of your system. Adjust the charging system to match the battery specifications. Install a low voltage disconnect to protect the batteries, and test the batteries in the field if possible. Thank you.
Thank you, Thomas.